Okay, so let's talk about how we can estimate the Bayesian approach, how estimation is done in the Bayesian approach. So again, here our aim is the same as the classical approach actually. So we have to estimate the parameter. In classical approach, you know how to find the minimum and unbiased estimator. We can define some good properties of an estimator, and then based on that we create best estimators. But here, since theta is a random variable, it has a probabilistic distribution, so we have to consider a different approach to be able to estimate using this approach. So here we define loss function. Loss function actually gives us the I have to say actually the measure of the difference between the estimator of a parameter and the parameter itself. Okay, so usually we are using in statistic linear squared error loss function, which is the difference between the estimator and the parameter, and we are taking the square of that, you know. But we have different loss functions, not just the square error loss function. So based on this loss function, we want to minimize the expected loss. Okay, so expected loss is defined as risk function. So our aim here is to be able to find the best estimator based on the minimum value of the risk. Okay, so we have to introduce loss and risk functions. So here we expect a good estimator. Let's define our estimator as delta x. Okay, so it could be x bar, summation xi, sample variance, or whatever that is. Okay, that yields an estimate of theta, which is close to the actual value of theta where the evidence happened. That is, so when we have a good estimator, so difference between estimator and the parameter will be small, maybe just 0 for the to be able to get the best one, but we never know. So for which it is highly probable that the error, so basically those functions are based on this, mainly based on this error function, this delta x minus theta. Okay, so we have to define some loss functions based on this principle, and where this expected difference will be minimum, our estimator delta x will be the best estimator. So we will assume that for each possible value of theta in the parameter space, and each possible estimate delta x in the parameter space, we assume that there is a number or a measure let's say there's a value or number L theta delta, okay, which measures the loss or cost to the statistician when the true value of parameter is theta and the estimate is delta x. When the true value of the parameters is theta and the estimate is delta x. So this is the cost of the statistician, cost of the statistician. So we want this cost or loss will be minimum. In statistics usually we use loss function, but in machine learning terminology they use cost as a loss. Basically they are the same. So the greater the difference between the estimate and theta, the larger will be the loss, and we don't want that actually. Will be the value of okay. So basically, since this is a measure, it should be positive, right? Or non-negative, let's say. If it is 0, then the estimate and the parameter are exactly the same. Okay, so it should be greater than or equal to 0 for each delta value, and equality happens for delta x equals theta case. Okay, and the expected loss is known as the risk function. Okay, so basically we want to minimize this risk and to find the value of delta which minimizes this expected loss or risk function. We use R notation for that. It's actually again between theta and delta x, and this is an expectation of L theta and delta x, and on parameter space we need to define this loss function. Okay, okay, so we need to find the minimum value of this. So basically we have to define L delta x, and maybe I have to use okay. Okay, so our loss function okay. So basically a statistician has to choose an estimate delta x for which, so this is in terms of the classical approach actually, risk or the expected loss is minimum. Okay, I will give the definition for the Bayesian approach also. So for each possible value of sample for the random sample, the value, another estimate actually, let's say, of x random variable of the bias estimator is chosen so that the expected loss which is the minimum value of x in the parameter space Okay, so we want to minimize this. So we have different loss functions. We don't have just one loss function. The most popular one is the squared error loss function, self. So let's talk about that. So possible loss functions. The first one is the most popular one, but it depends on the problem actually. So if you have a binary variables, basically square error loss function that helps that much. So you have to find different loss functions like hinge loss function. So you have to convert your system to a convex system. Then when you want to minimize the function, usually we are using derivative. And to be able to find the global maximum point, you have to choose a loss function for your problem that gives you exactly the global minimum or global maximum, whatever that is. Okay, so you have to choose your functions based on the problem. So if you have a linear function, or in many cases actually, so this square error loss function gives us the global minimum. But depending on your problem, you can consider different type of loss functions, and you have to consider the shape of the loss function when you take the derivative based on the expected loss. Loss or risk function. Basically, it should give you just one minimum point. Okay. Okay. So usually we use self for this. So this is basically make sure that we are getting the minimum value, choosing the best loss function part. So it makes so we will be sure that we are reaching the minimum. Okay, so this is the square error loss function, and based on that one, basically, if you choose this loss function, the minimum value attained at the mean of the posterior distribution. Okay, so expected loss, which is the risk, is minimized as minimum when we choose our estimator as the expectation of the posterior distribution. Okay, maybe I have to use a lowercase k. Usually I use lowercase k here. Okay, so the mean of the posterior distribution of theta. Okay, and the second one, the absolute error loss function Okay, so in this one, basically difference is just the absolute difference between the parameter and the estimator. Okay, so in this case, actually, expected loss or the minimum risk is obtained when we choose the estimator as the median. So these are the most popular ones. When delta x is the median of k theta x. Okay. Others, there are many others actually. So let me mention some. I'll give just the formulas for them. And so absolute error, but we are taking the kth power of the difference. K greater than 2. Another one. I'm sorry. Another one that I wrote here is this one. So it is 0, 1 loss function based on the difference. So if you have binary variables, these type of things can be good. So you have to define some C. Here's threshold. And giving no weight to the middle, but the high weight to the tails. Or the big value, big differences here. Okay. So basically, this is known as not 0, 0. This is a 0, 1 loss function. So 0, 1 loss function is used in testing problems. Usually. Okay. So this we talk about the classical approach loss function and how to find the minimum varies unbiased estimator, but also we can consider the Bayesian approach, and in terms of using the loss function, we can define the posterior distribution to find the estimator. Okay. So in terms of classical approach, finding the